Okay, welcome to the next lecture on network coding. This time we talk about storage. So far, I think you have learned a lot of things about transportation of bits and coded transportation where this is useful. But there's also a whole area where network coding can be used for storage. That was not our first choice. We started with transportation historically, but we also looked into storage. And I think if you remember one of the first lectures we had, I showed you something like this, ice cubes melting, right? Where I showed you what will happen if you have an uncoded system versus, I have to do it here, a Reed-Solomon or a network-coded, come on, ice cube. And this was just to visualize what happens here and to show you that our network code is really a robust thing also for storage. And I promise you that you will learn something about this in the storage lecture, and this is obviously today. So what we will do is to understand the basic things about storage, why this is needed, what network coding can do there. So I think you have seen that there was a huge growth in storage enterprises. There was something like coming up Dropbox, Google Drive, other things like SkyDrive, Box, iCloud, not so strong anymore, but Microsoft came up. And the good thing about this was there were some public APIs and usually REST-based, so that we could really build our own application on that. That you will see here today, that we really want to build something with our codes. We have Codo in the back, so why not doing something with that? And what we would like to tackle, there's something like reliability. You know, in data centers, you always have the problem that hard disk can break down. And one of the things that's very interesting is that the most hard disk breaking down while they try to repair other hard disks. So this is something NetCod told us. Also, you would like to think about privacy and security issues. And what was also our students at the time were really concerned about is how can we combine the free space that we have? So you get a little bit free space on Dropbox, a little bit free space on Google Drive, and they want to lure you into their systems, right? And you, of course, can use this space by storing your data a little bit on Google Drive, a little bit on Dropbox, but you have to manage it. Why not having something like a digital overlay that could help you to use this in a very easy way? So when you have then different options, the question is how to distribute the storage on the clouds. And our approach was always to distribute data on multiple cloud providers, right? From the user perspective, we have a tool for this, and we will use network coding to create something that is robust, fast in downloading terms, and secure in storing your data. And there are different things, what you can look at, something like data centers on the left, or user cloud storage on the right? They're called different generation, nothing to do with the cellular generation here. So a very simple example how storage can be done. You see here a server that has some data, and the data has 3 different segments, 1, 2, and 3. And while it tries to read 1, 2, and 3, and this is blocked, it would be great to have a copy of that, because in case you can grab the 3 from here, which is a totally copy from the other side, you can just quickly get the data. And then you are not blocked and stored in something about latency in this case, right? But you can do the same in saying, okay, instead of duplicating the whole 3 chunks, you can have one coded data here. And this could be a single XOR operation, right? When you go back to the interdigital network coding, here, this is what you see, a simple XOR. So if one of them is blocked, you just get the coded, you have the other 2, and then you do some processing. But even the processing can take some time, right? So now we deal, here we have extra cost in storage, here we have extra cost in a little bit in storage, but also computing. Depends on what you can do there. Of course, you can do even the same, using the same storage over here, use it in a coded way, because then there are more options where you prevent blocking. Okay? So let's make it a little bit more simple, right? Here we have one data that is represented by 10 data chunks, and we replicate it twice, right? So what happens, you have an overhead of 200%, and if you have a single error over here, you can ask one of the copies of 3, come over here and repair me. Okay? That is very easy, state of the art, something like this. And the other thing what you can do is you can make a code out of it. You leave your 10 chunks over here in a systematic way, so no coding, you're untouched, and then you come up with, let's say, 6 redundancy packets over here, right? So you have an overhead of 60%, not 200% as before. And this is called a 10-6 code. Facebook, for example, is using that, right? So if you now have a problem with packet number 3, you can, of course, repair that. How do you repair that? You need to get 10 packets out of the remaining 15, at least 10 of those, and then you can decode it. Okay? It's not just a copy, right? You have to do something. You have to get 10 out of the remaining 15, and then you can do this. So if they are in distributed places, your problem is really to take the data and bring it over to the right place. So this is one failure results in 10 traffic units. Can you improve the situation? I mean, even if you put more redundancy here, nothing will happen. You always need the minimum 10 to repair that. But what you could do is you can structure the repair mechanisms in a different way. For example, instead of giving all the 6 packets the way to code over the 10, why not doing something like this? It's called Sawbus, and there's a guy called DeMarcus who came up with some papers about that, and he nicely showed the network coding for storage is a great thing, right? And he said, okay, I keep 6 redundancy packets, 4 for the overall, and here you see 2 packets, 2 coded packets only over the first 5 and the last 5. What happens now, if you have a single error here, you don't need 10 packets to repair that. Now you need only 5. 1, 2, 3, 4, 5 will do the job. Okay? So if you have 2 losses over here, the problem is right away in this, you need to get 10 packets to repair that, because the local one will not help you here. So now the question is, how should we build this structure? So how many should think about the overall? How many should think about local areas? This depends a little bit about the failure structure. So if you know something about your failures, how they could happen, you can even place this one in a very nice way. Problem is a little bit, what happens if this situation will change? So sometimes this is good, maybe sometimes this is better. Why is this better? Because this can prevent way more errors or error situations. For example, here they can only repair that if you make a copy, for example. The extreme could be, let's make a copy from packet 1, copy from packet 2, and so on. Then you would have always a copy from packet 6, limiting the repair packet for the first 6, but you have no redundancy for the last ones. Okay? So this is not good. So question is now, what can we do there? First of all, where does it come from, right? It's not something that is now new with network coding. There's something called redundant array of independent disk, RAID system, right? That was something in the 80s where they had RAID systems 0, 1, 2, 3, 4, 5, very reasonable. This was redundancy in storage, and you find these papers from 1988, for example, from Katz, Patterson, and Gibson, where they said, okay, let's assume you have 4 different data blocks, right? And then you have a parity check here. And how do you create the parity check? Yeah, how you should read out. And this they did in the, if you have 4 disk, if you have 5 disk, how you do parity. Very interesting, and they were already concerned about how many read-write operations you have per disk and how many traffic you would have in the system. So all the questions have been there. The only thing is they considered this to be in one system, in one rack. Okay? Good. So let's go back and look at this in a more simple way, how coding can be done. So again, now I take only 2 packets, not this 10, right? If you have 2 packets A and B, there can be in different racks, in the same rack, it doesn't matter, but you can now make a repetition code of this, AB, 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 overhead 200% as before. If you now have 1 packet loss, what you see then is you copy 1 packet simply there. One of the two can help you over there. So what is the protection of repetition? In our case, 4 losses. If we kill 1, 2, 3, 4, we still keep the information. And 2 in the worst case, which means if you kill all of them, right, here, over there, there's nothing that is left over in the one, right? So, so in this case, it's just a copy, right? But what can we do in a different way? So if we, for example, look at a RAID system, we could say if you have an A and a B, you do systematic A, B here, and then you make a linear combination of A, B, or A plus 2B, right? A Reed-Solomon code could do this, not only to talk about network coding, any code could help you here. And then the overhead is only 100%. And if you lose now something, you still can repair it, right? It's very simple. You just take 2 packets, and then it's A plus B, and you have B, and out of this you can repair the A, right? So here, traffic to repair the losses is 2 units, and the protection is 2 losses. And now any 2 losses is still okay, okay? To give you some numbers for that, again here, if A would be equal to 2, B is equal to 3. Replication code, it's very easy. Now you have 2, K is the number of original data, N is the number of coded data. It's a repetition code, right? It's just a simply copy. And then you have the number of tolerable unit losses. In the worst case, it's 1. In the best case, it's 2, right? And the overhead is always N over K equal to 2x in this case. If you do a code, a simple parity code, you have A and B as the original one, you get 1 linear combination. Now you see number of tolerable unit losses is worst and best case is the same. And the overhead here is N over K 1.5. It's a little bit less, right? So there is a group of codes called MDS codes and systematic codes. MDS codes, they say you have the same number of tolerable losses, best versus the worst case, as we had before. There's the optimal overhead, but you buy in of extra computational complexity to perform the coding. Systematic codes, they have direct access to the content without doing any computation there. And the coded information only need with losses and in only, otherwise you would take the systematic ones, right? So in this case, you have a Reed-Solomon code with systematic codes, A and B, you copy them over, and then you have here 2 linear combinations. K equals 2, N equals 4. Now, what you can do then is A is 2, B is 3, then A plus B is 1. You take your lookup table, very easy. It's 2 plus 3 gives you 1. This is the result. And then A plus 2 times B is 3. So 2 times B is 3. 2 times 3 is 1. 1 plus A is 2. 1 plus 2 is 3. Okay? Now, you could kick out any 2, which one you want, it doesn't matter. I think the worst for you to think about is if I kick out the systematic ones. How do you reconstruct out of these 2 linear equations, A equal to 2 and B equal to 3? One way of doing that is to say, okay, A plus 2B, you can even say A plus B, so A plus B equal to 3. A plus B is 1, that is A, 1 plus B equals 3. So this is correct. A 1 plus B equals 3. 1 plus B equals 3. So B equals 3. 1 plus 3 makes this, and then you have B equal to 3. And if you have a 3 here, what plus 3 gives you a 1? It's 2. A equal 2. Okay, this is more or less how it works. So very easy to do that. And this is more or less the same what we have done in transportation. Nothing special there, right? And now, again, A and B can be of any size, right? A network packet 1 kilobyte, storage disk 1 terabyte, it doesn't matter, right? We will not discuss this. Normally in the storage we have the bigger packets here, right? The plus is very fast. The multiplication, you know how to do this. Use Codo, anything is fine.